Let's talk about acetals and ketals and how we make those reactions happen. We talked about in general terms that if we start with the ketone and we treat it with 2 moles of an alcohol with a acid catalyst, we will generate a ketal. Now, this right here is an acid catalyst. And the ones that we typically use for this reaction are sulfuric acid, or you can use, what's the other one? Toluene sulfuric acid, so TSOH. So both are really good acids. And so let me just say that again. This one right here is I'll just write it out so we can see it. It's para-toluene sulfonic acid. That's what that acid is. Those are the 2 common ones that we use as the catalyst to get this reaction to go. Now, I'm making a big deal out of this because the book and I don't see eye to eye, so I just want to make sure. We start with a ketone, we get a ketal. If we start with an aldehyde, then we have a acetal. Okay? Another thing to notice is that it requires 2 moles of alcohol, well, because we are adding those 2 ORs right there. Okay? So we need to know the mechanism on how this works. So I'm going to erase this board and we're going to jump into the mechanism. So the type of mechanism that I want to show you is just a generic one. Let's say we start with the ketone, and it doesn't matter what catalytic acid that we used, so we can just represent that with a generic acid. So the first step is, hey, you're adding an acid. So that means something basic is going to have to come and grab that proton. Now, every step in this acetal formation, or in this particular case, a ketal, is reversible. So now we're going to protonate. So we've protonated, that's a positive charge up there. You can barely see it on the screen. And then we have generated our conjugate base. So the next step, remember the overall conditions. You have the catalytic amount of acid, and then you also have your 2 moles of alcohol. So now what we have is we can look at our alcohol right here. And what did we just do with the catalyst? We have now activated that carbonyl carbon to be more electrophilic. So our weak nucleophile, you see it's just a neutral alcohol, now can come in and attack the carbonyl carbon. So I'm not going to draw stereochemistry just to keep things simple. So we are going to have our OH right there. And we brought the pi electrons up, so now that's neutral. And then we had the oxygen attack the carbonyl compound that is still bonded to the R and still bonded to the H. But now it only has 1 lone pair. We have an oxygen atom with 3 bonds, so that is going to be positively charged. So now we have to do a proton transfer. Let's use this one. And we generated a base right here, right? The conjugate base. So I'm going to take that conjugate base right there. And it's negatively charged. So I'm going to use it to grab and do a proton transfer step. And so that's going to give us OR, OH. Now, when that conjugate base grabs the proton, what did it also generate? Plus HA. It generated our acid back. Now, this species right here has a name. And when you have a carbon with a OR, so and a OH, we call that a hemiketal. Now, your textbook is going to call that a hemiacetal. But remember, we're starting with a ketone, so it's a hemiketal. But your book uses this for all of it, hemiacetals. So either one would work, but technically it's a hemiketal. So the generic form for a hemiketal would look like this. OH, OR, R, and R. And these R1s, those have to be alkyl. So that, if those are alkyl, then that is a hemiketal. If one of those R's is not alkyl, and it is a hydrogen, now if this is one of our intermediates, where did that come from? This species right here would have come from the aldehyde version right here. And so this generic formula right here would be called a hemiacetal. But we are dealing with the ketone. But you need to know those generic forms for molecules. Now, one thing about hemiacetals and hemiketals and why they're so important, one reason is the fact that that's the chemistry sugars use. So you can have sugars in our body. They can be in the keto form, or they can convert to hemiacetals and acetals, and that just influences the metabolic process of sugars and how they behave. So we may touch on that if we have time. Okay, so now we're at our hemiketal or hemiacetal, depending on who you're listening to. Now, what's the next step here? Well, we just generated the acid all over again, right? And our overall goal is to get 2 ORs on our molecule. So we're going to take this guy, take the alcohol, and protonate it. And when we protonate it, what happens? It becomes positively charged. And then we generated our conjugate base again. Now, why is that so important? Because now we've created water here, and we know water is a good leaving group. So the water is now going to leave, and we get, and the way we force it off to leave, we can bring in these electrons right here and form the double bond. So as that comes down, it's going to then look like this. Well, let's draw it with the proper geometry here. Double bond O, OR. That will be positively charged now. And plus water that just left. So this water molecule right here is that right there. Now this is protonated, or not protonated, it's the oxygen is partially, it is positively charged. So what does that do to that carbonyl? It activates it. And so another mole of water, not water, of the second mole of alcohol now can come in and react with it. So this is our second mole of alcohol. That guy's activated. So this can come in like so and give us we'll put the OR over on this side and then the ORH on that side. It doesn't matter, I'm just doing it to help with my drawings or the mechanism here. So now this oxygen is positively charged, so now we have to do a proton transfer. We just generated that in that step over there, so we have our A minus that can come in and do the proton transfer step. And that is going to give us our ketal. Pretty slick, isn't that? So there is our product. So that is our ketal. Now, one thing that I want you to be aware of is you see how these are all reversible arrows. So as you study this mechanism, most students are going to memorize it in this direction. But it's very good to know it in reverse. So how about you start with the ketal and do the mechanism backwards until you get back to the ketone. I highly encourage you to do that mechanism. Knowing how to do it forwards and backwards is important. And you may see those types of questions on standardized exams. Now, acetal and ketal formation is influenced by equilibrium, and we're going to talk about that after I erase this board. So let's take a look at equilibrium. So let's say if we have a very simple aldehyde, and we wanted to do the acetal formation. So we have 2 moles of ROH. And then we have our catalytic amount of acid. Equilibrium is going to favor the acetal. It's just small. They're the very simple aldehydes favor this. So if we draw equilibrium arrows, we could say at equilibrium, that's favored. But when you start looking at a little bit more complex ketones and you try to do this, you will get the ketal, but at equilibrium, it's not as great. Like, it's more favored, the reactants are favored more. But what if we really, really want this? Well, if we go back to our mechanism, what was one of the products for making this transformation? It released water. So if we want this reaction to proceed to the products, we can use Le Chatelier's principle to our advantage. As we do this reaction, as it's progressing, if we can remove the water, then that will drive the reaction to products. If you remove that, Le Chatelier's principle says equilibrium is going to shift to the right. And so you have these apparatuses where you can take off the water as the reaction's occurring to make this happen. So if you can remove water, if you remove it, then equilibrium is definitely going to be favored to the right. Now this next little bit is really cool, where we can use diols Look at this. So normally, under normal conditions, we use 2 moles of alcohol to form the acetal, right? Well, what if I change the look of the 2 moles of alcohol to just 1 molecule, like this? So that right there is a diol. It has 2 alcohol groups on it. It's 1 molecule, but it has 2 moles of oxygen atoms. So if you take that, you're going to form a acetal that looks like this. Just remember, what are acetals? It's ORs, right? Those are acetals. But you see how the R groups right here are attached. So those R groups are attached. So it's just going to be like that. And so that also follows under the definition of a acetal. Because we have our O, there's our R group, there's our O, there's our R group. Isn't that cool? So you can do this reaction with ketones as well and using a diol. It all works. What would be beneficial for you to do is to draw the mechanism for this. And the mechanism is exactly the same as what I did before. You're going to get these major intermediates. So if you react this with this, you are going to first form what? The hemiacetal. What would the hemiacetal look like? Well, you're going to have the, let's see here, the OH right there. So this oxygen is going to be this one. But this part of the molecule attacked the carbonyl. So we have that oxygen right here is that one. And then what's left over? That piece. So do you see how that is a hemiacetal? Because we have our carbon, 2 hydrogens, an OH, and an OR. And then that hemiacetal then converts into this. And how would that do that? Skipping some steps here, we're going to have a proton transfer step. That water leaves. All right, that water leaves, and that's going to be positively charged at the moment. And then this guy comes in and forms that. So in this particular problem here, I didn't do all the steps. But if you go back to the acetal formation mechanism, you will see it. Okay? So I would recommend do this diol and do the mechanism. Okay? That would be really a good use of your time. So acetal formation, when I showed you the mechanism, all the arrows were reversible, and we can use that to our advantage in organic synthesis. Acetals are reversible, and that's a key feature to this reaction. So on this topic of reversibility, let's say if I have a ketone and I treat it with a diol, and we're going to treat it with the catalytic amount of acid. So this would then turn into there's our oxygen, oxygen, boom. And there's our ketal. Now, if we want to go in this direction, what are we supposed to do? Because remember, if we just leave it as is, then the reactant is favored. Equilibrium says, hey, this way. So if we want to go this way, we have to remove water. So it goes that way. But what if I have my acetal, or in ketal? What if I want it to go back? So what do I have to do now? Well, you're going to have catalytic amount of acid. And if I removed water to go to this, how would I add water back? So if I add water and a little bit of acid, it is then going to go back to our ketone. This is so important to remember that this is reversible. Now, why is this so important? Well, I mentioned one, when we talk about sugar chemistry, we can see this happening. Also in organic synthesis. What we can do is, let's say we have another part on a molecule, something like this, and we want to do a reaction on X. But the reaction conditions that we want to use to react with X also reacts with the ketone. So what you can do is you can protect the ketone. And one way to protect ketones is to convert them into a ketal or an acetal. And now this will not react with the reaction conditions that you designed to react with X. And so you do the reaction to convert X into whatever you want, and then you deprotect the acetal back into the ketone. Isn't that cool? And so I'm going to show you an example on how that actually looks. But that's the idea of acetals, is they protect ketones and aldehydes from reacting when you don't want them to. So let's clean this up. So here's our example. So we have a ketone, we have a ester, and what we want to do is treat this molecule with a lithium aluminum hydride, which is going to, our goal is to reduce the ester into a primary alcohol. But there's a major problem with that. Lithium aluminum hydride will also reduce the ketone to an alcohol. So if we did this, our actual product that we would get would look like that. And that's not what we want. We want this. So how can we do that? So the goal is to protect this ketone so the lithium aluminum hydride doesn't react with it. So what we do first, and remember those are reversible, we protect the ketone with a diol. And that would obviously, you would need the catalyst, and then you would remove the water, and that would drive the reaction to look like this. And acetal formation does not happen to esters. So the ester is untouched. And now what you do is do your lithium aluminum hydride reaction. That's going to reduce your ester into the primary alcohol. And now you do the other step to deprotect the ketal here. And how do you do that? You add a little bit of acid, and then you add water instead of removing water in this step. And when you add water and a little bit of acid, that pops off, tacks on our ketone back, and boom, you have our product. So that's a major use of acetal/ketals. Okay. Now, in the mechanism, we learned about hemiacetals and hemiacetals and how that's an intermediate. Typically, you cannot isolate hemiacetals or hemiketals. They just react really fast to form the acetal and ketal forms. However, there is an exception, and that is if you have a cyclic hemiacetal or hemiketal. Cyclic ones are easier to isolate. And I want to show you what that would look like. Let's see, there's 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7. That's 1, 2, 3, 4, 5, 6. I added one too many carbons there. All right. We put a ketone there. Now, what can happen is if you add catalytic amount of acid, and these are going to be reversible. Do you see how we already have an alcohol on the ketone? And so what can happen here is that this is going to get protonated, and then protonated from the acid. That's going to activate it. And so let's just protonate it. I'm not going to show the mechanism. I'm going to protonate that, like so, from the acid. And what does that do? That now makes that more electrophilic. So now this alcohol can come in and form a 6-membered ring. Okay, let's see that. So if we number these carbons, we have, let's just number the oxygen 1, 2, 3, 4, 5, 6. And that would be 7, right? So it's showing me that number 1 alcohol is going to attack carbon number 6. So that's carbon 1, that would be carbon 6. So 2, 3, 4, 5. When that oxygen comes and attacks, it still has what? The hydrogen attached. And it still has the lone pair, so that's going to be positively charged. And then what's attached to carbon 6? It has this group right here, the OH. And then attached to carbon 6 is also this methyl group right here. And then what's going to happen? We're going to do another proton transfer step to get rid of protonated oxygen right here. So we'll do a proton transfer step to remove that. And there we go. This right here would be what? Our hemiketal. And that is, we can isolate that. So if the hemiacetal is cyclic, those are easier to isolate. Okay. Now, another prime example of cyclic hemiacetals or hemiketals are the sugars. So if you take glucose, I have it on the PowerPoint slide, so look at the PowerPoint slide or the image in your book. You can have a linear version of glucose, and you can have a cyclic version of glucose. And that cyclic version of glucose is a hemiacetal in that case. So look at your book for that. So that's really, really important, especially for biochemistry. So now we're going to shift gears and look at nitrogen nucleophiles and how they react and what compounds they make. Now let's take a look at reactions with aldehydes or ketones. Let's work with an aldehyde. So let's say we have an aldehyde here, and we want to treat it with a primary amine. Now this is very important that you understand the distinction. We are looking at primary amines reacting with aldehydes or ketones. And this is going to be under acidic conditions. So we're going to have an acid catalyst. And just like doing the acetal reactions, we want to remove water as the reaction proceeds. So Le Chatelier's principle will drive this reaction to the product. Now, when we take an aldehyde or ketone, treat it with a primary amine, what we're going to generate is something called an imine. And that would be like that. Now let me write it out. This species where you have the generic form, would be a carbon atom double bonded to a nitrogen. And that nitrogen has an alkyl group attached to it, R or an R. That is the generic form of a imine. Now, in our particular case here, do you see how this R right here can be a hydrogen? So it can be a hydrogen. So R equals alkyl and hydrogens. And this R group right here can also be a hydrogen. Same, excuse me, same with that one. So that is an imine. I need a pause. I'm losing my voice. So let's review here. Functional groups. We have something that looks like this. That would be called a amide or an amide, however you want to pronounce it. And then you have amines. So you have amines, amides, and imines. They all, when you say it really fast and not paying attention, you could get confused between these really easily just when you're hearing it. But when you look at them, you can see that they're drastically different. So this one right here would be what? A primary amine. Super important. We're using primary amines to react with ketones or aldehydes. Okay? So we want to look at the mechanism of how this happens. All right. So let's take a look at the mechanism to understand what's going on here. So we're going to just use a very simple ketone. And what are the reaction conditions? It says to add a primary amine. So we're going to do NH2, and to keep it simple, let's just do, what I want to do, let's do a primary amine. Okay, so you do the primary amine, you add the acid catalyst, and you're removing water as the reaction progresses. Okay. Now go back to the acetal formation. What was the first step in the reaction? The first step in the reaction when you were doing acetal formation was that the carbonyl oxygen was protonated by the acid. And we wanted to protonate the oxygen on the carbonyl so that we could activate and make the carbonyl carbon more electrophilic, right? Okay. But look at the first step of imine formation. You actually take the primary amine and you do this. And every step in this process is going to be reversible. So what we did first is this. And then we have our CH3 and our hydrogen. That's going to be protonated. That is our first step, which is different than the acetal formation. So the question is why? Why are we not protonating that oxygen first? It all comes down to the fact that you have a primary amine, which is more basic than the carbonyl oxygen. So when you have this amine mixed with all this acid, what's going to happen? It's going to react almost irreversibly with the acid to form this. The ammonium intermediate there. So we have like our ammonium ion here. So when we add the acid here, it doesn't go to the oxygen because of the primary amine. It's reacting with it to form the ammonium ion. And so what we have is small amounts. Most of the amine has been protonated, but there's still excess primary amine in the solution where you can have one that's not protonated that reacts with the carbonyl carbon. So that's why this first step looks different than the acetal formation. So throughout this whole process now, our acid is going to have this form, the ammonium ion form. That's going to be our acid. Okay, so that's the first step. So now what's going to happen here? Well, we can have another, because we're going to have excess amount of our amine present. So we will use that to deprotonate. So as we deprotonate that, we will have O minus, NH2, nope, not NH2, just NH. You know, I'll write it like this. I'll just put the H right there and then our methyl group right there. And so what did we also generate? We generated H2. There's our acid. Now do you see here? Now this can come in and grab that proton to protonate that alcohol. And so that would have a lone pair, that would have a lone pair. Now this species right here has a special name to it. And we call that a carbonylamine. Make sure I get this spelt right. Carbon and all amine. So that's a special intermediate that has a special name to it. Let's see here. So what's the next step here? So we have a reversal process. We need a proton transfer. We need to convert this hydroxyl into water so we can turn it into a good leaving group so it can leave. And so we're going to have our excess acid around. Let's see here. That one has 1, 2, 3, 4. So what we can do here is this is going to come and grab that proton so we can protonate that and turn it into water. OH, we just put that there. So now that's protonated, NH, CH3. Now that can leave. We can take the lone pair on that nitrogen, and that's going to help kick off the water. So now we have a nitrogen with a hydrogen attached and our methyl. So that's a nitrogen atom with 4 bonds, so that's going to have to be positively charged. And so water was expelled. That water came from this piece right here. So water leaves. And then we have this piece right here that hasn't been used. So that's going to act as our base. See how this acid loses the proton and now becomes this. Now that piece is going to be used to deprotonate. And so that will go here in a reversible manner. And now our product is going to look like that. And that class is Enamine. Right. Pretty cool mechanism. Now, I'm kind of getting on a soapbox now, but it is mechanisms. If you take and focus your time and energy on learning the mechanisms, then you can predict almost every reaction that's thrown at you. Also, remember, you see how all of these arrows are reversible. Can you take this amine, add some water and add some acid, and do it backwards? Okay. Because what's one of the products here? We're generating water. So if we add water and some acid, we can drive this back into the ketone. So make sure you learn these mechanisms forward and backwards. Now let's take a look at if you have a ketone or an aldehyde, and now you treat it with an acid catalyst, but instead of a primary amine, you do a secondary amine. What would we get? And what we get at the end of the day is another group with another new name, which looks like this. We now have a molecule that's called an enamine. And an enamine has a generic structure that looks like this. A carbon double bonded to a carbon, and that's going to be directly attached to a nitrogen, R. And then what else do we have here? That would be R and R. Okay. So let's take a look here. So if this is the generic form, if I label that carbon 1, that carbon 2, 1 and 2, you can see carbon 1 is attached to an alkyl group. That carbon right here is this guy right there, and that can be a hydrogen as well. So carbon 1 is attached to nitrogens. Those right there, those R groups, they have to be alkyl. And the mechanism is going to show us why. But then when we look at carbon 2, I have a hydrogen coming off here. So that one can be a hydrogen. And then this R group is that group. Now this R group can also be a hydrogen. So in order to form an enamine, it's these two R groups right here that have to be alkyl. So if we go back to the reaction, we are looking at when we take a secondary amine reacting with aldehydes or ketones, will give us an enamine. So we wrap it up. Now look at that. We have an amine, amide, enamine, and imine. Ugh. Things to keep track of, okay? So I'm looking down at the time. So what we're going to do then is look at the enamine mechanism next video. So that's what we'll do. Okay, we'll stop there then, class.